Hey, welcome back. The distance between 2 points in space given by point P, which will have an x, y, and z component, and point Q, x2, y2, z2, are given by distance equals square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Adding a third component just puts a third term underneath the radical. Find the distance between these two three-dimensional points. Okay, so I tried to sketch an x, y, and z axis. X is coming out towards you, the y, or behind you. Y goes horizontally left to right, and z is up and down. So let's jump in here. Distance is square root of 1 minus 2 squared plus 0 minus negative 1 squared plus negative 2 minus 3 quantity squared. Negative 1 squared is 1, positive 1 squared is 1, and negative 5 squared is 25. So that gives us a total of 27. Square root of 27 is the distance between point P and point Q. Q is actually underneath the x-axis. Point P is above. If you were asked to reduce, remember 27 is 9 times 3. Square root of 9 is 3. The other 3 you leave underneath. Definition: a sphere with center x, y, z, all subscripted with 0, has a radius r, and it'll have the equation x minus x sub 0 squared plus y minus y sub 0 squared, z minus z sub 0 squared equals r squared. Now, if you don't have these z components, then you've got the equation of a circle, but putting in a three-dimensional component to it where it's more like a basketball instead of just a washer, so to speak, or a coin. A coin's a better example of the circle, and then a ball is the example of the sphere. The midpoint is calculated by taking the average of the x's, adding them up and divide by 2, the average of the y's, and the average of the z's, and that's for midpoint. So we have distance, and that formula is at the top. Equation of a sphere, that's for any x, y, z on the edge of the sphere, but the ones subscripted with 0 are in the center of the sphere. And then we have a formula for calculating midpoint. Find the standard equation of the sphere that has 5, negative 2, 3, and 0, 4, negative 3 as endpoints of a diameter. Okay, so let's get the radius because that's part of the standard equation. We need to know r squared. Okay, so if these are the endpoints, let's calculate the midpoint. Remember, average the x's. 5 plus 0 over 2 is 5 halves. Average the y's. Negative 2 plus 4 divided by 2, that's 1. And then average your z's. 3 plus negative 3 is 0. Divided by 2, still 0. Okay, so now we're about to get the radius. You can pick either one of these two endpoints and use the midpoint you found, which would put you right in the middle of a sphere. The distance from an endpoint to a midpoint is going to be your radius. I just randomly picked this endpoint, the second one in the description. 0 minus 5 halves squared, 4 minus 1 squared, and negative 3 minus 0 squared. If you do the math, that's 25 over 4 plus 9 plus another 9. That simplifies to square root of 97 over 2. So our standard equation is going to be, and remember, the midpoint represents the center of the sphere, x minus 5 halves squared, y minus 1 squared, and z minus 0 squared, which is just z squared. If you square the radius, squaring removes the radical, but the 2 actually gets squared. So it's square root of 97 squared, that's 97, and 2 squared, which is 4. This is your standard equation of this sphere. Definition: let vector u have u1, u2, and u3 components, and vector v be this one. These are vectors in space, and we're going to let c be a scalar. The magnitude of u, or the length of vector u, you square each component, add them together, and square root the total. A unit vector in the direction of v, same as last video. We're going to take 1 over the length of the vector times each component of the vector. Example: find a component form and magnitude of vector v having initial point -2, 3, 1 and terminal point 0, -4, 4. Then we're going to find a unit vector in the direction of v. So first things first, excuse me, terminal minus initial, 0 minus -2, that's the first number. -4 minus 3, that's the middle number, -7, or the y value. And then finally 4 minus 1, that's 3, and that's the z component of vector v. The magnitude is 2 squared plus -7 squared plus 3 squared, all added together and square rooted. The sum of all three is 62. Square root of 62 is the magnitude. So it's just shy of 8. If you were to ballpark that, that would be 7 and some change. The unit vector pointing in the same direction as v is calculated by this process. And remember from a previous video, that's called normalization. 1 over the length of v, which was 1 over square root 62, make a direct substitution. Our vector in component form was 2, -7, 3, and then if you distribute, that gives you these three numbers. Definition: two non-zero vectors are parallel when there exists a scalar such that one vector is equal to some scalar times the other vector. Could be longer, could be shorter. They can even point in the opposite directions, but they only differ by some scalar. Example: vector w has initial point 2, -1, 3, and terminal point -4, 7, and 5. Which vector down below is parallel to w? Is it vector u or is it vector v? Okay, first things first, let's get the component form of vector w. If you're ever given an initial and terminal point, your first move is to get the component form. And that would be if you were to reset the initial point at the origin and maintain the same length and direction. Here we go. x2 minus x1 is -6. y2 minus y1, that's 8. z2 minus z1, that's 2. So this is the component form. This is where vector w would end in space if you were to reset the initial point at the origin. Now, let's notice that -6, 8, and 2, if you compare that to vector u, if you multiply everything by -2, you get exactly vector w. So we can say, because vector w is equal to -2 times vector u, they're parallel. So we can claim vector u and vector w are parallel. They have a scalar that makes them equivalent or equal. But -6, 8, and 2, when compared to vector v, It's pretty close, but not exactly. For example, -2, if you multiply by -2, you would get 12 times -2. You do get -16, but here's where it fails. -2 times 2 is not +4. So you do have to check all. There is no scalar for which vector w equals vector v for any scalar. So we can only claim that w and u are parallel. If v had a negative back here, they would also be parallel, w and v. Determine whether the points are collinear. If we were to plot all 3 points, do they fall on the same line? That's what we're trying to determine. Well, let's first get the component form of PQ. 2 minus 1, 1 minus -2, and 0 minus 3 gives us 1, 3, -3. Now, same point P, but let's go to R. 4 minus 1, that's 3. 7 minus -2, that's 9. -6 minus 3, that's -9. I purposefully picked a common point P, and also note that PQ, if multiplied by 3, gives you PR. So that tells us that PR and PQ are parallel and have a common point, so they're collinear. They all fall on the same line. Let's look at another example. Write the vector v in component form. Because it's an understood 3-dimensional, we have I, a missing j, and a k. 4i, missing a j, minus 5k. Find the terminal point of v given the initial point, -2, 3, 5. Okay, now this v here is the component form, it's the unit vector form that is terminal minus initial. Remember how we used to calculate it? We would take each part of the terminal point and subtract the matching terms from the initial point. We don't know the terminal point, so I'm going to assume that P is the initial point. I'm going to let Q represent the terminal point. Q1 minus P1 has to be 7. So Q1 minus -2 has to equal 7. That gives us Q1 of 5. Q2 minus 3 has to equal -1. That tells us Q2 is 2. And then finally Q3 minus 5 has to equal 3. Q3 minus 5 is equal to 3 when Q3 is 8. So our terminal point is 5, 2, 8. Terminal minus initial gives you your vector. Find the magnitude of vector v if it's written as -6i plus 2j minus 3k. You can think of this as x, y, and z components. Magnitude or length, it's going to be your first term squared plus your second term coefficient squared and third term's coefficient squared. 36 plus 4 is 40, plus 9 is 49, which has a square root of 7. So this vector has a length of 7 units. I hope this video helps out with your homework and your learning overall. If you have trouble, please reach out by phone, email, or stop by the office. And I wish you all the best and hopefully help you succeed. Thank you.